So MRI stands for magnetic resonance imaging, and it's an imaging technique that's dependent upon the magnetic properties, of components of our brains or other parts of the body, because MRI is used all over. But in the brain, oftentimes we're getting really good structural images from MRI because of the differential distribution of the hydrogen ion. It's different in white matter, for example, versus gray matter. It could be different in a tumor, for example, than in surrounding tissues. The way MRI works is you have to go in that big tube, right? You can't move. You got to stay very stable. Your brain is exposed to a very powerful magnetic field, and then the hydrogen ions all line up along those field lines. And then they pulse radio waves through your brain, basically, which interrupts the field, and the hydrogen atoms rotate. And then when they restore the field, they snap back into position, and a very distinctive pattern of energy is emitted that can be detected by the equipment surrounding your head. So MRI is, a very, very good structural imaging technique. It tells you, gives you beautiful pictures. It gives you sort of the best pictures, basically of the neuroanatomy. It can tell you something functionally too, like if there's a tumor in a very specific place, you could say just because of that structural image, that's what's leading to some of the very specific, sort of functional symptoms somebody may be experiencing. But MRI is also a very expensive technique, right? Because it requires very powerful magnets, impressive cooling systems. You have to have massive foundations have to be built sometimes, to house this kind of an equipment, and also, people who are specialists in the physics of MRI and are on staff, and that costs, a lot of money. So, it's an excellent, boon. It's been a boon to the work of, both clinicians and also researchers who want really terrific images and really clear understanding of neuroanatomy, and in some cases function as well.